This is Srikanth, working as assistant professor in electrical department. Here I want to discuss about theorems with AC excitation as well as DC excitation. Here we have some different theorems like diligence theorem, superposition theorem, reciprocity theorem, Thevenin's as well as Norton's theorems, and maximum power transfer theorem, Milliman's theorem, and compensation theorem. So with DC as well as AC excitation. DC and AC excitation, we have the different theorems. So for each theorem, I want to discuss about statements, overview, as well as procedure and formulas. For diligence theorem, in general, we have different circuits. In the circuits, we know the voltage drops, we know like branch currents and power. So coming to diligence theorem, in any network, so bilateral network, linear bilateral network, total power, so how much power we have for each branch or each element is equal to 0. Okay, if you check the statement, the diligence theorem states that the summation of power delivered for each branch, so delivered for each branch in our electrical networks. So particular time again, so we have, suppose we have the AC theorems, for each time we have different values. Here I have one circuit, so with DC or AC, so statement is same for DC and AC for each theorem. So here I have some voltage source, resistors I have, and suppose inductor also or capacitors. So depending upon different circuits, the power. So we know the V value and we need to know the I value. Same thing, V and I. V and I. Same V and I. Same V and I. The power, summation of total power is equal to 0. So the formula for this diligence theorem is summation of V and I. So voltages into your currents equal to 0. Sometimes you can apply the I square R formula also, you will get the same answer, but we need to follow the V into I formula only. Okay, V into I formula. For AC theorems, we have suppose supply and resistors and inductor and capacitors. So different values we know. So for each branch, for each element, I need to find out the V and I values for AC. For DC means it's very simple. It's very simple. So any circuit you can find out the I and V value. Coming to AC, we need to find out the impedance values. For each impedance, I need to find out the current as well as voltage. So for that I need polar to rectangular and rectangular polar values. So we need to find out the impedance value, we need to find out the I value, we need to find out the V value. So somewhat like a problematic. So we need to go for the different values with the polar to rectangular and rectangular polar values. For each branch, we require voltage and current. For here, branch means we have like a impedance. That means in impedance we have resistor as well as inductor and capacitor also. So depending upon the circuit. Okay. So this is about the diligence theorem. So once again, the statement for diligence theorem is the summation of power delivered is 0 for each branch. Okay. So coming to one more theorem, superposition theorem. It's also like one of the important theorem. So in maximum exams. So if you want to see like external exams, for any exam we have superposition theorem. Okay, like a theory part or problem part. Coming to superposition theorem, the statement is, so before going to statement, just observe the circuit here. So first circuit is voltage source I have and some resistors and one current source. And here I have I value. So when voltage source and current source both are acting, if you want to find out the I value, that I value is equal to, so again, now only one voltage source is acting and current source is open. Then I want to find out the same branch. So where I have the I value at that same branch, I want to find out the I1 value. And now third circuit, I have current source is acting and voltage source is short circuit. Voltage source is short circuit. Then at the same branch, I will find out the current. The current, suppose I2. So main current I is equal to I1 plus I2. If suppose I have like three sources, then the response at particular branch. So for using three sources, so source 1, source 2, source 3. So I1, I2, I3. So your main circuit current is equal to I1 plus I2 plus I3. Four sources means I1 plus I2 plus I3 plus I4. So depending upon sources, you need to find out the each source. So from the each source and find out the responses. So coming to statement, so any linear bilateral network, so that is a count for each theorem, okay, and more than one source, not one source, more than one source. So if you have the one source means not applicable for this superposition theorem. So more than one source, the response across any element. So response current, here I have a response particular branch is R3. So any one particular branch, the response. So here I have the current response. If suppose I want to find the voltage response, you can find the voltage response also with the same answer. Okay, and you can find the power on response. That answer also will get the same answer. Okay, some response. So more than one source I require and a response a particular branch. Then the summation of response. So summation means here I have the I1 value and I2 value. The summation of response from each source. So here I have the voltage source, here I have the current source. Then each source, so the remaining source is replaced with their internal resistance. So that means voltage source is short circuit, current source is open circuit. So same here. So the response from each source. So source is here voltage source, the remaining sources. So remaining source means we have the current source. If suppose we have a voltage source, in that voltage source we will go for the short circuit path. Here we have the current source, so we have the open circuit path. Coming to current source is acting, one more source. So then your voltage is short circuit. Okay. So this is about like a superposition theorem. Once again, your statement: any linear bilateral network having more than one sources, the response across any element is the summation of responses obtained from the each sources. So your superposition theorem is applicable for more than one sources. Okay guys, this is about the superposition theorem. Coming to one more theorem, that is reciprocity theorem. So reciprocity theorem also one of the important theorem. So reciprocity theorem means the responses. So where the response, that place is replaced with the source. So if you observe the circuit, you will get the answer. So here I have the voltage source and at this particular branch, I want to find out the current. So voltage source and my response is here. So at this branch, my response is suppose I. Okay, suppose my response is I. So at this branch, I want to replace the which source response that is. So from this source, I have the response. So you want to replace this source to here. So my source is here now, and I want to find out the source from which branch, the branch current. So this current is equal to your main branch current. So once again, here I have voltage source. So first branch, I have the voltage source, and I want to find out the R5 branch current. So I want to replace the source to which branch response we have. So this branch has the response. So I replace the source to here. So same place I replace the source, and I want to find out the response where we have the source. Where we have the source, I want to find out the response. So then, which response from first source, so replace where we have the source, that when we have the main circuit, which source, which response we have, that response is equal to your replace source response. Coming to statement, the value of current due to single source, here we have the V1, V value in any particular branch. So any particular branch is equal to the value of current in the original branch. So here the source is there, so replace with the current. So this original branch current, so equal to the original branch current, where the source is replaced when the source is particular branch circuit. So here I have the voltage source, here I want my response. So this is my current value. So using this source, this single source, I have the current value is equal to source replaced. So where the source replaced the original branch current, this current is equal to this original branch current, and the source is replaced where we have the response, where you have the current value. Okay, and you want to find out the unknown resistant value here, you can go for the V by I value also. If you find out the V by I, you will get the unknown resistance, so transfer resistance value. Okay, this is about the reciprocity theorem. Coming to Thevenin's theorem, so any bilateral network, so not only AC and DC, here DC or AC no problem. For any network, I want to find out the equivalent circuit. So any network, so we have like a different circuits. So voltage sources, or current sources, or resistors, or inductor, capacitors, so AC or DC. So any circuit convert to single network, that is equivalent network. Thevenin's theorem and Norton's theorem, maximum same. So Thevenin's theorem and Norton's theorem, maximum same. So coming to Thevenin's theorem, the whole circuit, so n number of sources and n number of elements, passive elements, is convert to single voltage source and series with one resistor. Okay, single voltage source, single resistor. For DC you can select resistor. Coming to AC, that is the impedance, single impedance. So voltage source, series with one impedance, and low resistor is common. So coming to statement here, so any linear bilateral network, AC or DC, okay, consists of several voltage sources and current sources as well as resistor or impedance. Can replace with just single circuits, that is voltage source series with your single impedance or resistor. Okay, connected across the load as it is, and we have some conditions. So I want to find out the voltage value. So for voltage value, open the low terminal. So here I want to find out the VTH or open circuit voltage. You can select open circuit voltage. Okay, so the voltage is measured across the low terminal. So remove the low terminal. So where is the low terminal? Remove the low terminal, and across that low terminal point and find out the open circuit voltage. The open circuit voltage is your VTH value. So for DC we have like a VTH and RTH. For coming to AC, VTH and ZTH. So that is impedance. And coming to when I find out the impedance or RTH value, ZTH or RTH value, we have again two conditions. That is, where the low terminal, just open the low terminal, and across the low terminal I want to find out the equivalent value, equivalent impedance or equivalent resistance value. There we have the voltage source and current source. So the voltage source and current source replaced with their internal resistance. So internal resistance means voltage source is short circuit, current source is open circuit. That's it. Okay. So this is about the Thevenin's theorem. Here I have like a small circuit. Voltage source I have and like 4 resistors converted to one voltage source and series with one resistor. Voltage source series with one resistor. So I want to find out like VOC value. For VOC value, this is your load resistance. So remove the load resistance across this point. So A and B point, and go for the one like a open circuit voltage. It's simple circuits. So open circuit means across the 5 ohms, which voltage we have, that voltage is your VTH value. And coming to RTH, so here same, open the low terminal, this low terminal between A and B point. Between A and B point, I need to have like a voltage. So low terminal, remove the low terminal and find out the equivalent value. So for that, we have voltage source or any current source. Replace with their internal resistance. The internal resistance. That means voltage source is short circuit and current source is open circuit. Okay. So this is about like a Thevenin's theorem. Coming to Norton's theorem. Again, same as your Thevenin's theorem. So we have voltage source series with a resistor. Any network converted to voltage source series with a resistor. Coming to Norton's theorem, current source parallel with one equivalent resistance. Current source parallel with their internal resistance. Okay. So coming to a statement, any linear bilateral network, same AC and DC, which are the Thevenin's theorem, same Norton's theorem also. Several voltage sources, current and resistors are passive elements. Just convert to single circuit, that is current source parallel with single resistance, that is Rn value and In value. So in Thevenin's we have voltage source series with resistor. Here current source parallel with resistor. For DC we have Rn value, but AC we have Zn value. We have impedances. And I want to find out like In value means for VOC or VTH, we need to go for the open circuit. Here we need to go for the short circuit. Same thing, but and find out the short circuit current. Here open circuit voltage. And Zn value is as it is. So same for your ZTH value or RTH value. So ZTH, RTH and Zn, Rn value same. But VTH is open circuit voltage and In is your short circuit current. You can select VISC also. Here VOC, open circuit voltage, here short circuit current. Okay, same procedure, but and final short circuit path current, here open circuit voltage. Okay, remaining procedure is as it is. Coming to small circuit, same circuit which we have earlier. So this is the low terminal. For current, we need to go for the short circuit and find out the I value. Coming to impedance and resistance. So voltage source is short circuit across the low terminal A and B. It's open circuit, remove the low terminal and this A and B point and find out the equivalent value. That value is Rn value. That value is RTH value. So for Thevenin's and Norton's theorem, maximum same. So but in Thevenin's theorem we have like open circuit. Coming to Norton's theorem we have the short circuit. That's it. And the current value and like voltage value. So open circuit voltage and short circuit current. Coming to impedance and the resistance values, equivalent resistance value. So we need to replace with the internal resistance the sources and open the low terminal and find out the between that terminal we need to find the equivalent value. So this is about the Thevenin's and Norton's theorem. Coming to maximum power transfer theorem. So which equivalent values we have like Thevenin's as well as Norton's. So voltage source series with the resistor and current source parallel with the resistor. So for equivalent resistor or equivalent circuit, we can find out the we will get like maximum power transfer theorem. So for this equivalent circuit, it's very simple. So when source resistance is equal to load resistance, so source resistance is equal to load resistance, then maximum power. So which power from source? So which power we have at source? That source from the source will get the maximum power to the load. Okay. Once again, I have equivalent circuit in that like voltage source as well as source resistance and load resistance. So for this, when source resistance is equal to the load resistance. So source resistance is equal to the load resistance, then maximum power delivered to the load from source. That's it. This is the statement from maximum transfer theorem. Same as for AC and DC, it's same. And if you want to find out the RS equal to RL, if you want to find out the RS equal to RL, you need to go for like I square R formula. So in that I square R formula, just substitute the I values and find out the maximum power. For maximum power, we will go for dP by dL value. Then if you go for the maximum power, we'll get like RS equal to RL condition. So when source resistance is equal to E equal to the load resistance, then we'll get the maximum power to the load. So this is a statement for maximum power. And if you want to go for like conditions, so which conditions we have for RS equal to RL, for this a different load values. Suppose here we have like a 5 ohms and here 10 ohm, 10 volts. Then just increase the load values 1 to 10 values, different values. Then find out the I as well as P values. But we require P only. Just find out the I and P values. We'll get very high maximum. If you compare those values here at RS equal to RL point. So here RL is 5 and RS also 5. RS 5, RL 5. Then we have the 5 hours. A remaining time, it's like increased then decreased point. So not 0. Okay, power not 0. So we have like decreased position. But we have the maximum. We have the maximum when RS equal to RL. RS equal to RL, we have the maximum power and we have the efficiency for the maximum power is only 50%. The percentage of efficiency for maximum power is only 50%. And find out the I value means using this formula. So you have only on closed loop. So closed loop means V by R. That is your I value. So here R is RS plus RL. Okay. So this is the general formula. And coming to P we have like substitute like a I square R formula. So I square means is V by R formula. So V by R means Vs by Rs plus RL square into your R value. R is at load point, RL, not again on RS. So for I and P, we have a particular point. We have a maximum power. That point is RS equal to RL. And coming to efficiency, it's like 50%. So output power by input power will get means only 50%. And the RS equal to RL. If suppose my value is RS equal to RL, the power P equal to Vs square by 4R. You'll see here also we have the formula. So Vs square by 4R. That is a maximum power formula using the maximum power transfer theorem. So statement is when the source resistance is equal to load resistance, the maximum power delivered to the load from source. So source to load, the maximum power delivered to the particular point when RS equal to RL. And it maximate, the power is maximate, RS equal to RL and efficiency is 50%. This is about the maximum power transfer theorem. And coming to Milliman's theorem. So Milliman's as well as you can say like parallel generation theorem. So parallel. So when we have the practical current sources, so not ideal current sources or ideal voltage sources, the practical sources. So practical sources connected in parallel, we can find out the equivalent circuit like Thevenin's as well as Norton's. So equivalent circuit means Thevenin's as well as Norton's only. Okay, like voltage source series with the resistor and current source parallel resistor. So here we have the practical voltage source. Practical voltage source means we have the internal resistance. So source having internal resistance, some internal resistance. That is your practical voltage sources. And practical current source means current source parallel their internal resistance. So if you observe the circuits here, so voltage source, practical voltage sources. So voltage source series with the resistor connected in parallel and lower terminal is as it is. Same thing, current sources connected in parallel. So this voltage source series with resistor can convert it to equivalent circuit like Thevenin's, and current sources we have the equivalent circuit, that is Norton's. Okay, for current sources, for coming to current sources, it's very simple to find out the equivalent circuit. So a particular node, so suppose this is my node, a particular node, this is my node, the currents, so here also like in between two nodes, the currents are connected in parallel. So parallel means a particular node incoming currents are equal to outgoing currents. So all are incoming. So all are you can add. For this circuit, I1 is incoming, I2 is incoming, I3 also incoming. So incoming means we are I value. I value is I1 plus I2 plus I3. Coming to R, so each resistor is connected parallel. Parallel means we have to use parallel formula. So 1 by R equivalent equal to 1 by R1 plus 1 by R2 plus 1 by R3. That is your R equivalent value. This R is nothing but your parallel resistor value. Okay, and coming to voltage sources, just find out the current here, find out the current, find out the current. Current means V by R value. So V means we have n number of V's. So V1 by R1 plus V1 by R. So V2 by R2 plus V2 by R3. This is your old like current values. So here current is V by R, here current is V by R, here current is V by R. Just add all values. So that is plus minus, just check the direction also. So values minus plus, minus plus, minus plus. So everything is we need to add. If suppose the direction is reverse, so negative, positive, then we'll go for the minus. Okay, here for this circuit we have, so same sign we have negative, positive, negative, positive, negative, positive, and like you can add those values. So V1 by R1 plus V2 by R2 plus V3 by R3, so on. Okay, that is your voltage value. So that is your current value, not voltage, that's the current value. I into R. So R is your again all resistor connected in parallel. Parallel means 1 by R plus 1 by R2 plus 1 by R3. So like we have the I value, this is your I value, and I into R value. If you observe this equation here for V, which we want voltage source series with resistor. For that I into R is required. For I is V1 by R1, V2 by R2, so on, into your R equivalent. R equivalent means again R resistor in parallel. Parallel means 1 by R1, 1 by R2 plus 1 by R3, so on. How many we have? So on. Okay, so we can write the equation like this also. So summation of V by R is V by R by 1 by R equivalent. That is your V value, not R value. That is your V value. So we'll get the V value. Coming to R, same. Which value we have? Same value from R. Okay. This is about the Milliman's theorem. So once again, the statement is when the number of voltage sources in parallel having their internal resistance and same as number of current sources parallel having their internal resistance. Here internal resistance means so voltage source with series, current source in parallel. Okay, can replace with single voltage sources or current sources like your Thevenin's and Norton's theorem. Okay, here voltage source series with equivalent resistance and current source with their equivalent resistance, single sources. Okay, so this is about the Milliman's theorem. You can say like parallel generation theorem. Coming to we have one more theorem, that is compensation theorem. So compensate, in that word we have a compensate. So when the circuit is like a somewhat some different problems. So I have circuit in some branch. I have resistor is some disturbance, like is increasing the values. Okay, I have a resistor in the circuit, and this resistor has some disturbance, some problem, some failure otherwise. So it's increasing. Some value is increased. So for that increased resistor, so I have a circuit, I require some particular current value, but the resistor value is changed. So for this resistor value changed, how much voltage I need to compensate for this branch? That is your compensate theorem. It's very simple. Okay. Here as a circuit is observe the circuit will get the answer. So voltage source and some resistors I have. The resistor I have. So for this RL branch, some disturbance I have, that is some resistor is increased. For RL branch, just observe guys, here RL branch I have, but RL branch current is increased. So for this branch, how much voltage I need to compensate? How much voltage I need to compensate for this particular branch? Okay. If you observe this circuit, you will get the answer. So I have a voltage source and RL branch. For this RL branch, I have some disturbance. So increase some value and I need to compensate some voltage. So this is your main circuit. For this main circuit, I need to compensate some voltage. So this voltage, which current we have, suppose at source branch, which current we have, at load branch, you have same current. So when you compensate some voltage, so why I need to compensate means, suppose the value is increased here, then automatically this IS value will be changed. So not equal to this source current. So main circuit source current. So source current change and load current value also change. Am I right? When the circuit is some small value increase means automatically every branch. So every branch current will be changed. So I will compensate some voltage. So if suppose I will compensate some voltage here, then which source current we have? So same source current and same current value will get at load point. So how much voltage I need to compensate? That what is the voltage value? That voltage value is so main circuit current. So what is your general current? So actually my output is suppose 2 amps. Here I require 2 amps. Okay. But somewhat is increased, so some disturbance is there. So that current into how much resistor is increased. How much resistor is increased. That resistor value. That is the compensate voltage. I into R. Okay. So the I. So I require 2 amps means I have a 2 amps current into. So here 2 ohms is increased. So 2 ohms is increased. So 4 volts I need to compensate for this branch. Then the values. So the which value we have like previous same we will get this answer. Okay. So for that the compensate theorem we need to prove means. So we have the voltage source and find out the current. So main circuit. So main circuit and find the current and increase resistor. So somewhat increase resistor. For that I need to find out the I dash current. So some different current. And I need to prove means here I want to prove means the compensate voltage, that is I into your increased resistor value. That is your compensate voltage. There I want to find out the delta value for this your source, which how many sources we have. The source is replaced with their internal resistance. So here I have the voltage source. So I replace with their internal resistance. That is short circuit. Then find out the I dash current. So this I delta current. So this I delta is equal to I minus I dash. Okay guys. Here in some books they have like direction downwards. This also downwards means we have I delta is equal to I dash minus I. Okay. I delta is nothing but I dash minus I. This is the proof of compensate theorem. Okay. So in any exam, anywhere you want to prove means, so no need to go worry about these 2 circuits. Up to here is enough. So we need to find out the current value. Okay. We need to find out the I dash value. So when the resistor is increased, then what is the current value? And here at last we need to find out the delta value. So I delta. So for that we need to compare some voltage and replace the remaining source with their internal resistance. Yeah, coming to statement. So any linear network we have resistor. So where is the load resistor? That is also uncoupled branch carrying some current. So here I have the RL branch carrying I current. It changed to R delta. So R delta is changed. Then all branches current will be changed. So all branches current will be changed. Then assume that ideal voltage. So some voltage I need to assume. So here we have the VC. So for VC, the current value is that which current we have from main circuit into your R delta value, that is your VC value, with replaced with your load resistor is replaced with RL plus R delta. So this is about like compensation theorems. And coming to AC. So coming to AC, we have some problems. For DC, the theorems is very simple. Coming to AC, we have some problems. So what is the problem means? Suppose here I have a circuit. For this circuit, I want to find the current. So any method I want to find the current. For that, so for this branch, I want to find out the current. Now current means we'll go to the mesh analysis. Generally, we have the loops. From loops, we'll get the current value. Suppose the direction, this is my direction. Same direction or reverse direction. Same direction means where I of t will get like I1 plus I2. Suppose the reverse direction means we'll get like I of t is equal to I1 minus I2. So in general, now loops means I need the mesh analysis. Mesh analysis means I require the voltage drop. So what is the voltage drop here? What is the voltage drop here? What is the voltage drop here? That means equation we get from two equation. We need to find out the values I1 and I2 values. Somewhat difficult. So why means here we have the imaginary values. So here we have the imaginary in J form. So for that J form, we need to convert into polar to rectangular. Again, we need to go for different manners. So for any circuit, if you have like a difficult equations, so big equations or 3 equations or 4 equations, then go for the Cramer's rules. For AC, the Cramer's rules is like a simple way to find out the equations. So for Cramer's rule, just convert those equations in matrix form, and in that matrix form, suppose I have two equations means I have I1 and I2. So del of del I1 by del of delta and del of delta 2 by del of delta. So for using this equation, you get those values I1 and I2 values. For del of delta, the main equation cross multiply means again we need to convert it to polar to rectangular to polar, and we will get the delta value. Same thing. Delta 1 means replace the values, your I1 values, and with your equal to values, and delta 2 means I2 values, replace with equal to values, and find out the del of delta values. We'll get like I1 and I2 values. So here main rule is we need to find out the polar to rectangular and rectangular to polar. If suppose here I have an example. So superposition theorem. So we know the statement. So more than one sources. Here I have the voltage source and here current source. A current source, voltage we have. So this current source and this is my voltage source. So two sources I have. So I have the response in this branch. Now when the current source is acting, the voltage source is short circuit, and find out the response here. And the voltage source is acting, current source is open circuit, then find out the response. So for DC means it's very simple. Coming to AC, again two loops. Here two loops. Here the current source. So here the source means we have the like a I1 and I2 value. I1 as well as I2 value. Suppose I want the I1 value means source current into opposite resistor. So what is your opposite resistor? Capacitor. So one XL value, JXL value minus of JXL value by your total resistor. So resistor and capacitor. So R minus JXL value. You can directly substitute those values and get the I1 value. Coming to I2 value, so it's like inductor is open. Here we have only one loop. So Vs by your I2 value is Vs by, so resistor and capacitor both are in series. Only one loop means both are in series. So R minus JXL value. So we have the I1 and I2 value. Summation of I1 plus I2, we have the I value. Like superposition, using superposition theorem and find the I value means you can use this method. It's very simple. So no need to worry about the like equations if you know the logic. So here I use like current division rule. Here we have like single loop means it's open. So no need to worry about the inductance value. So we'll get the answer. Okay guys, this is about like theorems AC and DC. So for AC theorems, if you have any queries, just comment me in comment box. Any problem, if you have the, like any problem, just comment me in link which problem is required. So I will solve those problems with another video. Okay, thank you for watching my videos. If any queries, comment me in comment box. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.